This is AP Precalculus Notes for Topic 2.15 Semi-Log Plots. So a bit of reading, but we've looked at logarithmic scaled axis in the past, and now we're going to look at it again to look at semi-log plots. So a semi-log plot is where we have the y-axis scaled, not the x-axis. X-axis is always the same amount, like 20, 20, 20, 20. The y-axis here is scaled linearly, which means you're just adding the same amount. So this is not a semi-log plot. This is a semi-log plot because you can see that we are changing proportionally. We're multiplying at each step, multiplying by each step on the y-axis and adding on the x-axis. So the definition for my semi-log plot, my very basic definition is that if I have some sort of x-axis, this one is being added and this one is being multiplied. So we've seen this before, where we're looking at the population of English Americans in the United States between 1620 and 1820, and t is equal to 0 this time right here, or here is equal to 1620. So on our normally scaled axis, where these are added and these are added, you can see that it's an exponential model. You can't really see any change happening here, and you see that it kind of explodes off here. But when I plot it on a semi-log plot, where the y-axis has now been scaled logarithmically, you can see that after you hit right about here, 40, it kind of just continues as a straight line. And here's the key thing. Whenever you see a straight line, whenever you see a linear function, that means that it's probably modeled by an exponential function. So you can say that this is going to be exponential after it turns into a line around year 40. So we see, yeah, left is the normal scale, right is the semi-log plot. So in this example, use the features of the semi-log plot to justify why an exponential model is appropriate for the population of the United States. And you can just say, well, look, maybe not from 1620, but after 40 years, you can say after 40 years, which is going to be 1660. After 1660, the semi-log plot is linear. So exponential is the best model. That's all you have to say. It looks like a line with a semi-log plot, therefore it's exponential. That's as much as you have to say. So we've got another example. Let's read. After Mr. Passwater tells yet another one of his hilarious math jokes, it begins to spread around the school. The number of people, P, that have heard the joke after 2 minutes is graphed on the semi-log plot down here, where the vertical axis has been logarithmically scaled. It goes by 10, 100, and then 1,000. So we are changing proportionally at each step. We are multiplying on our y-axis. Which of the following functions could be a model for P? So this question is kind of hard until you learn a bit of information that I'm going to put on the third page of these notes. That Mr. Passwater put on the third page of these notes. But one thing to always note about exponential functions is, well, first of all, they have to be exponential. So I have a variable and exponent, I have a variable and exponent. That's a log function, so that's not right. And that's a linear function, so that's not right. This function is plotted on a semi-log plot, and it looks like a flat linear function. That means it's going to be either that one or that one. Do you notice the difference between B and D? One of them is multiplying the two, and the other one is adding the two. Adding the two typically means that if I have a normal plot, this would be like a normal exponential function. It shifts it up, so it would look something more like this, where the horizontal asymptote is not the x-axis. That does not happen very often. So right off the bat, I'm suspicious of adding and I'm leaning towards multiplication, but I need to have some sort of mathematical justification for that. So here's how I'm going to justify this. And again, this is a lot harder than it needs to be. There's an easier way in a second. But I'm essentially saying, hey, I'm going to have my P function, which is going to be equal to, it's essentially a line. It's y equals mx plus b, right? It's mx plus b, mx plus b. I guess it's not really x though. T is my variable. Let me swap out the x for a t here and say this is m times t plus b. The problem is the y-axis has been scaled logarithmically. So what I'm really doing here is I'm doing log of that p to get this equation. Now to undo a logarithmic equation, you just rewrite it in its form, right? This is technically log base 10. By the way, this base 10 will always match the scaling. What are you multiplying by each time? I'm multiplying by 10. Therefore, this base is 10 as well. I'll go over that a little bit later as well. And to undo this logarithm, you change its form. So if I say, okay, 10 is going to be the new base, so I'm going to come down here and write 10 for my new base. And then I'm going to switch these two. So it's going to be 10 to the power of mt plus b, and that's going to be equal to, and then this p goes on to the other side, right? So it's going to be equal to p. So this is the function p that we're looking for. It's that thing right there, which, and again, this doesn't really give you the answer right here, but it will tell you if you have any multiplication or addition. Because whenever I have addition happening up here, what I really have is properties of exponents. This is really saying, I'm going to come over here in blue and say, this is really 10 to the power of mt times 10 to the power of b. That's what p is really doing, because properties of exponents, if I multiply the same base, I'm really adding those exponents. So I'm really taking two quantities that I'm multiplying. I don't know what the value of m is. I don't know what the value of b is, but I know that this thing probably is 2. And this thing, 10 to the power of m, probably is 2. So you get 2 to the power of t, and then an operation that is multiplied by 2 to get our value for p. And again, how did I know that? I don't, but those are the only options. It's either a 2 adding or being multiplied, and it's clearly being multiplied just because of how logarithmic functions work. So that's my kind of wishy-washy explanation that the answer is D. Typically speaking, you are going to be multiplying as a general rule of thumb, though. We're on to the second page. So when, again, an important note, when we're logarithmically scaling the y-axis, we're not changing the y values. We're just changing where they show up. We're not, like 40 is going to stay 40, 60 is going to stay 60. We don't change these values. They stay the same. We just change if they are on a line or if they're on a curve because of how that y-axis is scaled. And the x-axis should always be linear. So as a reminder, when I have my axis, I'll draw my picture yet again. When I'm talking about my x-axis, this needs to be added over and over. When I'm talking about my y-axis, it needs to be multiplied over and over. So let's read example 3. We have a table right there, and which of the following graphs could represent these in a semi-log plot? So first of all, it needs to be a semi-log plot, which means the y-axis needs to be scaled. Take it from 1 to 2 and from 0 to 1. I'm constantly adding on this y-axis. So I'm doing plus 0.5 to get from here to here. I'm doing plus 0.5 to get from here to here. I'm doing plus 0.5. I'm constantly adding over and over, which means this is not even a semi-log plot. This y-axis needs to be multiplied. And the x-axis is actually being multiplied, which is kind of funny. The x-axis is the log plot. So this is backwards. So it's not A because that's not even a semi-log plot. What about B? B is a semi-log plot because you can see as it gets higher, these numbers get closer and closer together. So B is actually a logarithmic plot. So it's probably that answer. All we have to do is verify that that data has been graphed appropriately. So I'm going to go to 1. I go to 1, and I go up to a height of 40. I go up to a height of, well, there's 10. my point should be way up there. That is an incorrect point. So B, while it is a semi-log plot, it is not the correct data here. What about C? So C, again, is this problem where this is just a normal plot. This is constantly going up by 50, so plus 50, plus 50, plus 50, and then over here it's plus 1, plus 1, plus 1. This is just a normal plot. It's not even a log or a semi-log plot, so it's not C, even though the data is probably graphed correctly. And then therefore, I think by process of elimination, the answer has to be D. Let's analyze why. First of all, it's a log scale on our y-axis because you can see to get from 1 to 10, to get from here to here, I'm multiplying by 10. To get from 10 to 100, I'm multiplying by 10. To get from 100 to 1,000, I'm multiplying by 10. So I'm constantly multiplying on our y-axis. And on the x-axis, I'm just adding 1, adding 1, adding 1, adding 1, adding 1. If you constantly add on the x-axis and multiply on the y-axis, that is a semi-log plot. Now we just have to verify, are these data points correct? And you can say, okay, I need to graph 1, 40. So I come down here, I go to 1, and I go up to 10, 20, 30, 40. So this is 1, 40, and I assume that the rest are correct as well. The correct answer is indeed D. All right, then we move on to the hardest and last page of the notes, page 3 of 3. Example 4, we need to actually plot the following. So plot 0, 200 and label it A. So 0, and then I go up 10, 100, 200 is right there. So I'm gonna come here and graph that and say that's point A. Then B is 1, 25, so there's 1. I come up 10, 20, and then half of 20 is going to be right there. So 25 is there. What about C? C is 2, 7, so there's 2. I'm going to go up. This is 1, 2, 3, 4, 5, 6, 7. I zoomed in, so I'm going to have to do that again. So there's 1, 2, 3, 4, 5, 6, 7. And that's going to be point C. And then point D is 3.2800. So okay, what is this? What are these tick marks meaning? So I have 1, 2, 3, 4, 5 jumps, which means each of these jumps is dividing this into 5 pieces, or if you want to say one piece of 5 is the same thing as 0.2. So each of these tick marks is actually 0.2. So 3.2 is this spot exactly right here, and I'm going to go up to 800. So there's 2, 3, all the way up to 10. There's 100. I need to go up to 800. So here's 200, and only zoom in here so I don't have to rezoom. So here's 100, 200, 300, 400, 500, 600, 700, and 800. There's our point. So that's going to be the point D. And then finally, we have the point E, which is 4.6. We know that each of these tick marks is a 0.2, so there's 4.2, 4.4, 4.6. So there's 4.6, and I go up 1.5. Well, I'm already at 1. You can see on the y-axis that this is 1, so I need to go up 0.5. So half of that is going to be right here. And that's going to be with the point E. All right. And how do we, this is, I think, the hardest part out of everything. How do you turn an exponential function that's shown on a semi-log plot that we have happening down here? How can you actually show the linear equation of that line? Because it is technically an exponential equation. So if I want to show what the equation of that line is, if it's just a linear line, then you have to take the log of each piece. And you've kind of seen that happen on example 2. But essentially what we had happen here is we had like a times b to the power of x or something like that. And then what we did was we took the log of that function to change it from exponential to linear. So if I take the log of that, whenever I multiply the insides, I'm adding the outsides, and then you have log of a right there, and you have log of b right there, and again this x comes down in the front, so it's being multiplied by x. So it really comes from that old formula of our default exponential equation, and you just take the logarithm of it, and it looks like that. And you can choose any n that you want. Usually it's picked for you on the graph. Like, for example, to get from 10 to the power of 0 to 10 to the power of 1, I'm multiplying by 10. Whoa, that's multiplying by 0. Multiplying by 10, therefore my n value is going to be equal to 10. Again, to 10 to the power of 1 to 10 to the power of 2, I'm multiplying by 10, therefore the n value is 10. And again, the number that's in front of the x, it says it right here, the number in front of the x, log base n of b, that's the number in front of the x, is the slope, because anything that's in front of an x in a linear equation is a slope, and then that other number is the y-intercept. So the y-intercept is going to be log base n of a. All right, so, I mean, it seems understandable at this point, I hope, and then actually applying this can be tricky. I don't think I've ever done it before. This is my first time applying it as well. So we have the semi-log plot above in example 3. We need to write an equation for the linear model. So it is exponential, but we want to find the equation of the line, and it's going to look like that, of that form. So what do we have happening here? I'm going to find slope. My slope here is going to be the change in y over the change in x. So the change in y is actually the log of the change in y. So let me modify this. On a semi-log plot, it's really log of the change of y. And then my change of x has not been scaled logarithmically, so it's still the change in x. So that's what I'm really doing here. I'm going to say, okay, I have a y coordinate. I'm just going to choose that point and that point. It doesn't really matter. You could choose that point and that point. You could choose that point and that point. You just need 2 points to do your slope down here. You'll get the same answer regardless, I hope. It is my first time doing it, but I assume that's the case, just like it is in normal algebra. So my x coordinate is 1. So I'm going to do, let's do 1 second. And I'm going to do 2 and put it here. And I'm going to say, okay, my change from here to here, I went 1 to the right. And this x, or this y coordinate is, there's 10, 20, 30, 40. So this is the y coordinate 40. And then here's 50, 60. That y coordinate up here is 60. So what I'm doing here is I went up to log of 60 from log of 40. So that's my change, log of 60 minus log of 40. And I need a calculator for that. So let's go ahead and do my split view. Let's open up my calculator. I need to do a second plus 712 to clear everything. All right, so on the top of my fraction, in the parentheses, is going to be log of 60 minus log of 40, okay, that's the top, notice the parentheses, divided by, and I'll start my parentheses, 2 minus 1 is just 1. I didn't need to do the divide by 1, but whatever. So there it is, and I get my slope. So this slope is, again, we're approximating now, so I'm going to round it 4 decimal places because logs, I want more precision, 0.1761. And I'm going to store this because I'm worried that this is not going to, or this is going to come back in part B. Yeah, so I'm going to have to turn my linear model into an exponential model. I want this stored. So what value did we just find? We found the slope. The slope, as we know, is the number in front of x. So I'm going to store that in variable b for my calculator so it makes sense to me. So I'm going to say store that as alpha, and then I'm going to hit apps to hit b. So that's stored in b. All right, how do we find the other value? How do we find the y-intercept? Because the problem here is we don't have a y-intercept. If it gave us a point here, we just take the log of that point and we'd be done. Say, okay, oh, it's log of 20 or something like that, because that's 10, that's 20. We could just say log of 20 and we'd be done, but I don't have a point here. So I'm going to use my old algebra skills and say, hey, I have this thing right here. And I know what this is. That value right there is a 0.1761 if I take a log of b. So what I really have, I have y is equal to 0.1761x plus this value that I don't know. I'm just going to go ahead and call all of that a for now. I know it's technically log of a, but I don't want to write that over and over. So how do I solve for this? Well, we have an x and y coordinate that I can plug into this. I can say my x and y coordinate is, I can choose any of those points. I'm going to choose this one because it's nice and easy. The x coordinate is 1, the y coordinate is 40. So I'm going to come down here and say the x coordinate here is 1, and the y coordinate is 40. And I can plug everything back in, 0.1761 plus a. And then finally I can solve for a, and I can just multiply 1 times this, and I still get the same answer. And I can move this on over. I have a feeling that this y coordinate is log of that y coordinate though, isn't it? Because all y coordinates are log of that. So I was wondering, like, how is this number so big? It's because I didn't take the log of it. So let me be careful here. If I take the log of that number, then that will work. Okay, so I'm going to say log of 40 minus b. So I'll hit alpha apps b. And I get a is equal to 1.4260 if I'm running to 4 decimal places. All right, so I have my a, I have my b, and now I think I can just put them both together and then I'm good to go. I can say, hey, my linear equation is, I'll write my final answer, y is equal to my slope, 0.1761x, plus my b, which I have in my calculator right there, plus 1.4260. All right, so I'm going to box that to let my teacher know I have found the linear model. And now I'm going to use that to write the equation. Okay, so I should store that answer. I'm going to store that answer as alpha math, so I'm going to hit store it as a, and I just need to figure out what that is. So essentially what I've said, I know I've done it a little bit wishy-washy, and I said that that is the value of a. Technically, what we just found right there, that's technically log base 10, so I'm just going to say log of b. That value is log of b, and this value over here is technically log of a. I was just writing a as a shorthand notation. So in order to find a, I need to undo that. So let me rewrite those equations down here. I really had log of b is equal to 0.17609, and I had log of, wait, let me do this off to the side so it makes more sense. I'll say log of a is equal to 1.4260. Oh wait, I rounded that one to a 1 here. I was just reading off the calculator, so it's a little bit off, but that's okay. So in order to change this, I'm going to say technically this was log base 10, technically this one was also log base 10, and I'm going to change its form. This is in logarithmic form, let's change it to exponential form. Keep the same base, and then you switch these two, b and these two flip-flop, right? And then I'm going to say b 10 to the power of 0.17610, or whatever it was, 1761. That's my b. And then over here, 10 to the power of 1.4260 is equal to my value of a. And I just do that. And okay, so let me make some room for myself. I wrote a little bit too low. I can say 10 to the power of, and I can hit alpha b. That's, oh my God, it's exactly equal to 1.5. So I'm going to say 1.5 is equal to b. That came out really nicely. And a is equal, is this also going to be nice? Let's see. Let's say 10 to the power of a, alpha a, and I get 26.6 repeating. So this is going to be 26.6 repeating, which is a fraction. That would be divided by thirds. It would be, it's really close to 78 thirds, because I think 78 divided by 3 is 26. Yeah, so it's 78, 79, 80. It's 80 thirds. This is 80 thirds for A. Or you can just leave it as 26.6 repeating. It doesn't really matter. So what do you do with those? You're going to write it of this form. We know the form. It's always multiplying. You can say my equation is y is equal to A, which was, I was going to say 78 thirds. It's 80 thirds. I like my fractions. Times B. B was 1.5. 1.5 to the power of x. All right, very cool. So that concludes our notes for AP Precalculus on semi-log plots for topic 2.15. Here's the third page, second page, and first page. Thanks for watching.